Welcome to our lesson on complex numbers. Today, we'll explore what complex numbers are, their components, and how to perform basic operations with them. Let's start with the definition. A complex number is any number that can be expressed in the form of plus IB, where A and B are real numbers, and I is the imaginary unit that satisfies I squared equals -1. In this form, we call the real part of the complex number, denoted as re of z equals A, and B the imaginary part, denoted as im of z equals B. Let's see an example of a complex number in standard form, also called Cartesian form. Consider z equals 3 minus 2i. In this case, the real part is 3 and the imaginary part is -2. One of the most intuitive ways to understand complex numbers is to visualize them in the complex plane. In this representation, the horizontal axis corresponds to the real part, and the vertical axis corresponds to the imaginary part. Our example, 3 minus 2i, would be plotted at the coordinate 3 minus 2. Now, let's look at operations with complex numbers. First, let's explore addition. If we have two complex numbers, z1 equals a plus ib, and z2 equals c plus id, then there's some z1 plus z2 equals a plus c plus I times b plus d. For example, if we add 3 minus 2i and 1 plus 5i, we get 3 plus 1 plus I times minus 2 plus 5, which equals 4 plus 3i. Let's visualize this addition in the complex plane. Here's our first complex number, 3 minus 2i. And here's our second complex number, 1 plus 5i. To add them, we can use the parallelogram rule or simply add their coordinates. The result is 4 plus 3i, which is at the point 4, 3. In our complex plane. Subtraction works similarly to addition. For two complex numbers, z1 equals a plus ib, and z2 equals c plus id, their difference c1 minus c2 equals a minus c plus I times b minus d. For example, if we subtract 1 plus 5i from 3 minus 2i, we get 3 minus 1 plus I times minus 2 minus 5, which equals 2 minus 7i. Next, let's look at multiplication. When we multiply two complex numbers, a plus ib and c plus id, we get a c minus bd plus I times a d plus bc. This result comes from distributing the terms and remembering that I squared equals -1. For example, if we multiply 3 minus 2i and 1 plus 5i, we get 3 times 1 minus minus 2 times 5 plus I times 3 times 5 plus minus 2 times 1, which equals 13 plus 13i. Geometrically, multiplication by a complex number can be thought of as scaling and rotation in the complex plane. For a complex number a plus ib, its modulus or absolute value is the distance from the origin, which equals the square root of a squared plus b squared. Its argument is the angle it makes with the positive real axis. When we multiply two complex numbers, their moduli multiply, and their arguments add. Now, let's look at division of complex numbers. To divide one complex number by another, we multiply both the numerator and denominator by the complex conjugate of the denominator. This gives us a plus ib, divided by c plus id equals the fraction with numerator, a c plus bd plus I times bc minus ad, and denominator c squared plus d squared. For example, if we divide 3 minus 2i by 1 plus 5i, we first multiply both the numerator and denominator by the conjugate of the denominator, which is 1 minus 5i. This gives us the fraction with numerator 3 minus 2i, 1 minus 5i, and denominator 1 plus 5i, 1 minus 5i. After simplifying, we get -7 over 26 plus I times -17 over 26. Finally, let's discuss the complex conjugate. The complex conjugate of a complex number z equals a plus ib is defined as z bar equals a minus ib. It flips the sign of the imaginary part. A useful property is that the product of a complex number and its conjugate gives a real number. Z times c bar equals a squared plus b squared. For example, if z equals 3 minus 2i, then its conjugate z bar equals 3 plus 2i, and their product is 3 minus 2i, 3 plus 2i, equals 9 plus 4 equals 13. We can visualize the complex conjugate in the complex plane. If we have a complex number z, its conjugate z bar is obtained by reflecting z across the real axis. This is because conjugation only changes the sign of the imaginary part, keeping the real part the same. Let's summarize the key operations with complex numbers for addition and subtraction. A plus IB plus or minus C plus ID equals a plus or minus C plus I times B plus or minus D. For multiplication, a plus IB times C plus ID equals a C minus BD plus I times a D plus BC. For division, a plus IB divided by C plus ID equals the fraction with numerator, a C plus BD plus I times BC minus AD, and denominator, C squared plus D squared. And for the conjugate of a plus IB equals a minus IB. Complex numbers are essential in many areas of mathematics, physics, engineering, and computer science. They help us solve problems that would be impossible to solve with real numbers alone. With these basic operations, you now have the tools to handle arithmetic with complex numbers.